Hi, welcome. On this video, we will learn how to derive half-time equations for a first-order reaction. But first, let's remember the definition for half-life or T1/2. So it is the time required for the concentration of a reactant to decrease to half of its initial concentration. Having said that, we can get started. So now we're going to work on the first order reaction. So this is our concentration time equation. And okay, so this numerator, it's going to be the same as ln of 2. You can do it in your calculator and you'll get this number. Here we have our concentration time equation for the first order reaction. As we can see, we have two different formulas, but actually they are the same. So a formula can be written in different ways just because we have different properties, especially with natural logarithms. So this one is given on your workbook and this one was given on the table. So let's see how the formula that was given in our workbook can look kind of this one. So, let's see what we have. So we have ln, natural logarithm of the current concentration. And then we want to solve for t, right? So the first thing you want to do is bring the ln of initial concentration towards your left side. So you would have ln of current concentration minus ln of initial concentration. And that would equal to negative k times t. And from there, well, this is a personal preference, I guess. So if I like to cancel out the negative signs because I don't like working with those. So I would just go ahead and multiply everything by the negative sign. So I will get positive kt, k times t, equals, so this one will be positive. So ln of initial concentration minus, okay, so this one was positive, so now it's going to be negative. So we would have ln of current concentration. Okay. Okay. And as you can see here, we can apply a property from natural logarithms. I don't know if you remember this from your pre-cal class, that whenever you have ln of a minus a ln of b, you can just put it in this form. So actually we're going to do that so it can kind of simplify things. So kt would equal to ln. So our A, in this case, it's going to be our initial concentration. So let's go ahead and put it in that format. Initial concentration over our B, which is current concentration. There we go. So we're solving for t. So t would equal to ln of initial concentration over current concentration and this over k. So let's see, is it similar to this equation? Yeah, so it's really similar. So as I told you before, there are a lot of ways of having the same formula, but it can look a little bit different, but it will still be the same. So right here, they have current concentration on the top and initial concentration on the bottom, and they have a negative sign. So we actually got like kind of the inverse. So we have everything positive, and we have initial concentration on top and current concentration on the bottom. Yeah. So we're on the right track. So now that we solve for T, we want to solve for a half-life equation. So yeah, remember that T, it's going to be T1/2, and our current concentration, it's going to be initial concentration over 2. So let's go ahead and change our formula. Modified, well, it's basically kind of the same, but for half-life. So we would have ln okay, so we have initial concentration then over, so remember like all of the numbers like could have a 1 as a denominator, so it wouldn't change, like 9/1, it's 1. So let's go ahead and put a 1 as a denominator for our initial concentration, because we will do the quote trick again. So I'll make this parenthesis longer. Okay, I'm gonna erase it because it's screwed. So let's do it a little bit bigger. Okay, cool. Okay, and then it was over the current concentration, but now that we're solving for half-life, our current concentration, it's going to be our initial concentration divided by 2. So let's go ahead and plug it there. And this all over K. Yeah. So let's go ahead and do the quote trick again. So I'll choose another color. So we would multiply the ones that are on the outside, and those will be our numerator, and the ones inside are going to be our denominator. So ln of 2 times initial concentration over initial concentration. So as we can see, we can cancel. Okay, so let me over K, right? So as we can see, we can cancel out the initial concentration because we have it on the numerator as well as in the denominator, and this is true because they are multiplying, so we can go ahead and do that. So our final half-life equation for this first order reaction, it's going to be ln of 2 divided by K. And this will be our half-life equation. Okay, so as we can see, the half-life of the first order reaction is independent of the initial concentration of the reactant. So as we can see, there's no initial concentration on the half-life. Here. So measuring half-lives at different initial concentration is one way to distinguish between a first order and a second order reaction, which we'll be seeing later. So let's go ahead and see the table to see if we got the same answer. Well, the same formula. So yeah, yay, we got it. If you like this video, I would recommend you seeing part 3 in order to see the remaining half-life equations. And if you haven't seen part 1, I would recommend you to do so. Please subscribe to Hydrogen Bonds Are Fun and follow us on our Instagram page. Thank you.